These are the notes for how we find the equations of parabolas using our new definition involving the focus and the directrix. So we spent almost the huge first part of the first semester dealing with parabolas. And we graphed them, we talked about x-intercepts, y-intercepts, all of that stuff. Right now, we're actually going to go back and redefine parabolas using a definition of distance, just like we just did circles using definitions of distance, Pythagorean theorem. So the definition for a parabola using distance is that a parabola is the set of all points, x and y, that are equidistant from a line L that we call the directrix, and a point not on the line that we call the focus. So let's look at an example. So remember, distance, Pythagorean theorem. So we're going to be dealing with distance again. So let's look at an example. So I've been given a focus, I've been given a directrix, and I have this arbitrary point. So I need the distance from the point to the directrix. The important thing to remember here is that that distance has to happen at a perpendicular. It has to reach the directrix at a 90-degree angle. And then I also need the distance from the point to the focus. So two distances. Now, the distance from the point to the directrix is relatively straightforward because I haven't gone any x direction. I haven't moved left or right. I only have a y direction happening here. So I only need a change in y. For the focus, I am changing an x and a y direction, and so for that, I actually am going to draw in a right triangle, and I'm going to need a change in y and a change in x. So let's set this up. So the first thing that I'm going to find is the distance from xy to y equals 3. And you can think about this as Pythagorean theorem, or you can simply think about this as the distance, the change in the y's. So the change in the y's is going to be y minus 3. I then need to find the distance from x comma y to the focus, 1 comma 7. For this, I need to actually do the longer process of Pythagorean theorem. So I have L1 squared plus L2 squared equals hypotenuse squared. I'm going to go fill in up here. Remember, my L1 and L2 are the changes in the x and the y. So my changes in my x are x minus 1 squared, and my changes in the y are y minus 7 squared. Sorry, I lost track of something here. And that is a distance squared. I do have a mistake up here. So let's go back to this for a second. So even though my, oh, no, actually, I'm going to adjust this slightly. So in order for these distances to be, this is just the distance. So in order for us to compare the two distances, this distance and this distance, I need the distances to either both be distances or distance squared. So what I'm going to do is I'm going to plug this distance in for d. D is the same length. That's the whole purpose here, is that I want the equation where those two lines are the same distance. So I have x minus 1 squared plus y minus 7 squared equals x minus 3 squared. I've substituted in my d value into the equation I had for my distance from x to y, xy to 1, 7. So this is going to possibly feel a little odd, but I am going to transform this equation. Whoops. There we go, that's better, y minus 3. I'm going to transform this equation, but I'm not going to touch my x numbers at all. So when I transform this equation, I'm going to leave x as x minus 1 squared. And instead, I am going to expand out my y's. So expanded out the y's is y squared minus 14y plus 49 equals y squared minus 6y plus 9. I am then going to move I'm going to move everything except for the x minus 1 squared over to the right-hand side. So I still have x minus 1 squared equals, when I subtract y squared, the y squareds cancel. So now I'm going to add the 14y, subtract 49y, and I still have on this side a negative 6y and a positive 9. I'm now going to combine like terms, so I get 8y minus 40. I still have x minus 1 squared. I still have x minus 1 squared. And now I want this to look like the parabolas we worked with in the first semester. So I want this to look like a y minus a number with nothing else around it. So to do that, I need to factor out an 8 from both of these terms. And then I'm going to multiply both sides by 1/8. So on the left-hand side, I get 1/8 x minus 1 squared. On the right-hand side, I get y minus 5. Now this looks a little bit different than the form we used in the fall. However, it kind of is a little bit nicer in terms of what we're doing with circles, because now I can look at this and I read off the vertex very similar to the way I read off the circle, the center of the circle. So my vertex here is 1, 5. Now let's go back and look at my graph with this information a little bit more. So when I'm looking at my graph, my vertex is on my parabola somewhere on that parabola. And because the vertex is going to be between the focus and the directrix, it actually turns out that the vertex falls on the same x value as the focus and literally right in the middle of the directrix and the focus. So that happens right there. And so let's check. This vertex is 1, 5, and the vertex we found using algebra is also 1, 5. So I can see it both in terms of the graph where my vertex is and in terms of the algebra.